This is the start of the recording. I am. Am I unmuted? Yeah, I can see. Yeah. Okay. Cool. Yeah, I'm just talking at the beginning of the recording, just so that those who tune in later can adjust their volume. And we will start in 130 seconds. All right. Good morning, folks. Still 10 more. And all right. Good morning. It is Wednesday, April 15th. Let us get going here. Okay. Um, just please a reminder, it is Wednesday, but there's the Thursday quiz, so please think about that. I know it's been hard to sort of get a rhythm going, kind of all semester long, on some level, and this, of course, change hasn't exactly helped that. But so I'm just trying to remind you about that. This point, be sure to keep current with WebWork. I need to, I think, say a word about this. So I know that sometimes WebWork can be frustrating. I also know, um, or can imagine, that this format makes things just extra difficult. Please make use of office hours, but perhaps more importantly, keep current with WebWork. Let me say what that means, because I think there's a misunderstanding. I would have said this no matter, I mean, this would have been true in the first half of the semester as well. But if you start the assignment that is due today on today, so if today's the day that you start the assignment that's due today, you are being very late in the process. That does not work. It's not sustainable. It will lead to a lot of frustration, especially if and I get that work schedules and so and all all kinds of other things. Watching out for um, a family member that you would not normally be responsible for, or so on, complicates the story. And so I actually did do something about that. I just didn't mention it. I'm actually going to mention it right now. So if you look back, if you not that you have to do it. I mean, you can call me out on it if you want and check. But like this is what I did. I just didn't say anything about it. If you go back to the syllabus website, I made some modifications on it back during spring break, but I also put a link to the original. Um, and here's the thing: the if you look at the original schedule for the WebWork, uh, the chart of WebWork dates there, like if you work on even then, if you worked on the assignment, started an assignment the day it was due, that would have been late by uh, as much as sometimes five class not five actual calendar days, and it just depended because we meet 4 days in a row. Sometimes things were off from that. Sometimes it was 3 days away. Sometimes it was 5 days away. But the thing is, even then, that's starting an assignment the day it's due is problematic. What I did was, as you know, the lecture schedule all got pushed back 1 week, but I pushed the WebWork schedule by more than a week. It was actually by a week and one extra day. And you might say one extra day isn't a lot, and I get it. It's not a whole lot, but there are these pros and cons. I mean, you have no idea the sort of agony of like what do I do? So this extra day compared to what happened in the beginning of the semester is to recognize that people's schedules are different and need to do things a little differently, but if I did an even additional day beyond that, if it was a week plus 2 days, then we'd be talking about literally all assignments being due 1 week after the topic was covered in class. So as it stands, some days of the week, what happens is right now things are due 6 calendar days after we first talk about them in class. Nothing is ideal. Everything has pros and cons, but once we got to the point where it was 7 days after, that became too much of an extreme. Because as it is, there's a lot, that happens in a class day, and we've got to, yeah. So I hope you understand where I'm coming from with this. I'm not trying to be harsh, but at the same time, I'm trying to keep people on pace, and I know that's harder to do, but the thing is, I want you to go back and look at the syllabus and look at the original. I mean, not the original, but like in the new version of the schedule, there is you should start WebWork assignment number blah on such and such date. You should go by those dates, because if you don't, I'm not saying you have to finish it on that date either, right? I've never said that throughout the semester. But you should consider starting the assignment on the date that is suggested. Otherwise, you run into this trouble of getting really frustrated. So please do the best you can to avoid that situation. I get you've got a lot of things. I know that this is not your only class and so on. But if an assignment is due every day, I would suggest that you stick to the schedule that's originally posted. The extra days are there so that if something comes up, and now like the extra time compared to even in the past, so that if you need to, you can visit office hours at the learning center. You get what I mean? Like that I keeping current on WebWork, just to summarize, is not about starting the assignment on the day it's due. That's now 6 days later than it should be on most days of the week. Okay, this is the question I'd like to work on today as a full class first. So you have a rectangular box with a square base. It is to be made with 5 cardboard sides and a plastic lid. If the box must be 100 cubic centimeters, and cardboard is $6 per square centimeter, and plastic is $11 per square centimeter, how cheap is the cheapest box? So I will comment that this is our last in-class day of talking optimization, so I've picked a more challenging question. We've been kind of ramping up to this, and normally what I know that this question has a lot of moments where people would want to ask questions, so please do, but at the same time, it's maybe because of the format, it's hard to just sit and pause until somebody keeps asking. So I will try to speak slowly, keep the pace okay, and I will also, in the pauses, I'm going to try to anticipate any questions. It's not what I normally do. I've been told don't answer questions that people don't ask, but I think this is a little different. So I'm going to try to answer questions that I think might be coming up. But that said, if I don't address your question or you want something repeated, just please ask it. Okay. All right, so the first step in any of these optimizations is to scan through and look for quantities. So rectangular box with a square base made with 5. Okay, 5 is a number, I guess in some sense technically quantity. I would rather not call the 5 cardboard sides and the one other side, which is made of plastic. I would not like to say that 5 or 1 or 6 are quantities here. Like every box has 6 sides, right? So like let's not call that a quantity. I'm thinking more like by quantity I mean like something that's going to get assigned a variable or shows up in one of these equations, these geometry formulas or something like that. So you see here next 100. That's, by the way, the problem doesn't say this is a volume, but it doesn't say in the words volume, like the word volume doesn't appear, but it's cubic centimeters. So the units here are giving away that 100 is a volume. Now, you might say, okay, well, should we use a V as a variable for volume when we already know the number is 100? I'm going to go ahead and say, let's call volume here a quantity because volume appears inside a formula for box. So we'll have that quantity of volume. We got $6 per square centimeter, $11 per square centimeter. So these are cost. These are not actually direct costs, but they're rather cost rates. They're letting you know per square centimeter, it's going to cost you this much. So I'm actually going to call these numbers not quantities. They're fixed. It's sort of like if you go to the store, this is how much you have to pay for those pieces. You'll see how these fit together. But then take a look here. It says how cheap is the cheapest box. So how cheap is the cheapest box is talking about what's the cost. We want to make the cost small. So cost here is a quantity. So take a look. What I'm trying to get at is I'd like to say that volume is a quantity, that cost is a quantity. It is an important quantity because it's the thing that we're going to minimize. And because volume is going to bring up length, width, and height, let's call those quantities here as well. Okay, so step one was to not only identify the quantities, but to identify which quantity is going to be optimized, so or what's the objective as it's called. So in this question, it says it's how cheap is the cheapest box. So that's just another phrasing for make cost small. Right? And this is actually fairly realistic as a problem type. Now, you might have a business where, okay, maybe cost of cardboard is not $6 per square centimeter. That's kind of expensive cardboard. I mean, maybe the real story is cardboard costs like, that per square centimeter in reality, but it's just we can do the same concept without having numbers that are that awful. So I wanted to pick whole numbers just because it just makes things a little easier to write down and think about. That's all. But like you can imagine even a business where you're selling a certain product and you're not really interested in boxes, but because you're, Apple Computer or whatever, right? And you want to make your boxes sleek or whatever, like that's an important part of your process. So it actually matters to companies that are not interested in selling boxes themselves, that maybe the packaging needs to be right. And so you want to maybe balance things like presentability and at the same time make it cheap still. So these are important. These are actual questions that businesses need to deal with, like making boxes cheap, even if they're not in the box business. Okay, so we need to minimize cost here. Step one was up to there. What are the quantities? Right, so these two bullets here. Yeah, what are the quantities? And then which quantity do you want to maximize or minimize? And in this question, it's C. We'll minimize C. Now the next part is to take the quantities and write down any equations that relate these together. So first of all, there's this nice one, right? Volume is length times width times height. So yeah, V is equal to LWH. And in fact, we can go ahead and we were told in the question that the volume is 100. So we might as well replace the V that appears right there with a 100. And if you do that, you'll have 100 is equal to LWH. Another equation, we should deal with the cost. Now this is the thing that we previewed last week that is admittedly challenging. So this is not the entire cost. It says 11 LW plus, and then there's still a part missing because I want to just focus on this right now. So I want to talk about this lid. So you've got this box. Let me draw the hidden sides here as well. You've got this box, and there's an L here, maybe W there, H there. I mean, the point is, if this is the height, the lid costs $11 per square centimeter. So this lid right there that I'm shading in right now, that top, the area of that rectangle doesn't involve H, right? Because H is perpendicular, H is the height. So this rectangle on top, this shaded rectangle, you see another copy of it on bottom, and that's LW. So right here in parentheses, LW is the area of the rectangle. But if you recall last week, what you do is you take that area, and then you need to multiply by In this case, it's per unit of area, per square centimeter, it's going to cost you $11. So you should multiply that by 11. I hope this makes sense. If this works out here, like the point is this LW, the units on the LW is in square centimeters, right? That's what an area is, right? It should be a square centimeters or square inches or something like that. The 11, by the way, the units on it, sorry for how it's written up here, but the units on this is dollars per square centimeter. And so here, your square centimeters on top and bottom cancel. And so then this total underlined thing, 11 LW, 11 times LW, that is the units on that is in dollars, and that makes sense for a cost. We doing okay with that? I'll just pause for a moment, make sure we're okay with, we took the surface area of just the top, as the top is more expensive than the other 5 sides, right? The plastic is more expensive here. We took just the area of the top and then multiplied by $11 because the, plastic lid. So here we are using part of the surface area. This is not right, like, and now that's just the top, but then there's these other 5 sides. So there's the 4 around. I shouldn't have marked that way. Now, okay. So you've got like the right side and the left side. I just shaded the right side. You also have the front and the back. So how do I do this? Maybe I'll shade the front this way. You have the front and the back as well. So think about it. So, oh, there's also the bottom. The bottom, by the way, is another LW, right? Just like the top. So there's an LW. And then for the left and right side, I guess you've got an HW, right? An HW and another HW. So there's 2 HWs. And then for the front and the back, there's an L times H in front, and there's an L times H in back. So all in all, those 5 sides, the area of those 5 sides is in parentheses right here. So LW was to represent the bottom, right? That area should, this LW first is like the area of the top was also LW. And then the LH is for the, maybe the left and the right side, and then the WH was maybe for the front and the back. So I hope what you're seeing here is underlined here is 5 terms. I just collected some like terms here. There were originally 5 terms for the 5 remaining sides, the side that wasn't the lid, the 5 sides that are made out of cardboard. But again, underlined there is an area. And so what's underlined currently is in square centimeters. And we should take that number of square centimeters and multiply by, it's $6 per square centimeter. So when you multiply the units on the 6 were in dollars per square centimeter, the units on this larger underlined text was in square centimeters. So then the overall thing here, past this plus sign, is in dollars. So we've got the cost of the lid. I'll just maybe get rid of some of this underlining for a moment. We've got the cost of the lid. We've got the cost of the remaining 5 sides. The cost of the remaining 5 sides are kind of all together because we just kind of incorporate it all at once because it's all made out of cardboard. So $6 per unit of area, and then that area is, in both cases, areas in parentheses. A surface area is the relevant surface areas in parentheses. The other point I should maybe make right now is that there is a plus sign here. Sometimes people are like, what do I do? But you got to think about this, right? So like you need to pay for the top and you need to pay for the other 5 cardboard pieces. So it makes sense to add. If you were to subtract, for instance, that would mean like you pay for the top, and then the rest of it, like not only do you get for free, but somebody's paying you when you buy cardboard, right? So that wouldn't make sense, right? So you got to think if this is addition or subtraction or multiplication or what makes sense. You've got to pay this, you also have to pay that. So you got to pay both, and so you should add those things together. Maybe one other comment I'll make is that this cost here, I mean, as written here, this is not the same as surface area. What we've done is we've taken pieces of the surface area. So like LW was just the area of the top. And then there's the LW for the bottom, and then the other 4 sides, so LH plus LH plus WH plus WH. Just the underlined pieces all together. If I added the 2 underlined things, that would be the surface area, but you see how the surface area is kind of broken up because part of the area has a different rate of cost than the other, and so we had to multiply by the appropriate multiplying factor in order to get the total cost. So that here is the cost. I want to pause, see how we're doing, see if there's a question. I tried to address all the the main things, but I bet I missed something or said something confusing. So I want to just wait for a moment, see if we're doing okay. Okay, in all these optimization problems, what we need to do is we need to solve for the objective. So solve for C. Check it out. C is already solved for. It's on one side of the equation by itself. And then differentiate. The problem with trying to differentiate what's underlined here is there are three variables. There's L, there's W, there's H. So we can't differentiate yet. We need to start eliminating variables somehow first. So let's do that. First of all, we're told in the question originally we have a square base. That's helpful because normally when you draw a box, L, W, and H are normally allowed to be all different, right? L, W, H. But if you have a square base, this is saying not the height, but the other two things, L and W, are the same, right? Square base. So square means this side is the same as that side. And so in this case, it's L and W. L is equal to W. This is useful because this means that everywhere in the problem you see an L, you can now replace it with a W, or everywhere you see a W, you can replace it with an L. I happen to prefer writing W's. My L's look a little too much like ones, so everywhere I see an L, just out of convenience, I'm going to replace every L I see with a W up from above. I mean, I'm not going to modify the top of this slide. I'm going to write new things below, so you kind of see the evolution of the work. In fact, even in the font that the computer gives me, the L looks too much like a 1, so I had to do something special to get sort of a more loopy script style L here. So first of all, take a look at this is a way that we wrote the volume, right? Because we plugged in the original volume equation is boxed there, and then after the word so, you see we plugged in 100 for the volume. So there's this volume equation, but look, if you replace the L right here with a W, then you have 100 equals WWH, or W times W times H. I just rewrote the W times W as a W squared. So applying the fact that L is equal to W, here's a new way to write the volume equation. But not only do we make use of L equals W to simplify this equation, right? So the volume equation went from 3 variables, LWH, now down to 2 variables. But the other place this is helpful is take a look at the cost equation right over here. I wrote this down there. And every L gets replaced with a W again. So 100 LW, 100 WW, or in other words, 100 times W squared. Same deal, right? Replace every L with a W. I'll just let you stare at it. This is probably one I don't need to overtalk. Every L gets replaced with a W. You know what? You don't have to do the following simplification, but maybe it helps you to see that now that we've replaced this L here with a W as well, every L is a W right now, then take a look. You've got 2WH, 2WH. You don't have to collect like terms, but why not? Let's make things as nice as possible before introducing derivatives. So collect like terms, and you have a 4WH. Also, you might as well distribute the 6. So 6W squared, and then 6 times 4WH should be a 24WH. Oh, by the way, if you have a 6WH, you could collect like terms with the 11WH. Sorry, with the 6W squared can be combined with the 11W squared, so that's why there's a 17W squared. And then why the 24? Remember I just said earlier there was a 6 distributed to a 4WH, and so that becomes a 24WH. Does that look okay? I hope the algebra seems okay there. So whether it's this format or this, both underlying things are equal. But we still can't differentiate. Now, this is better. Underlined over here, all 3 underlined things are the same. They're all the costs. They're all literally equal to each other. It's just the cost that's up at the top has 3 variables, and then the 2 underlined down in the same line, it's also cost, but at least there's only 2 variables, just W and H. But the problem is it's still 2 variables. So it's better we went from 3 variables to 2 variables. Now what? We still want to differentiate. I mean, I want to differentiate this, but we can't because there's 2 variables. So what can we do next? And I'm going to wait. I'm going to ask somebody to volunteer this information. Like, what can we do? Is there any information that we've written down that we haven't really done anything with yet that could help us out so that eventually we could write C in a format so that after the equal sign, there's not two variables, both h and w, but maybe only one variable? Is there something we haven't used yet? Something that might be helpful? Something that we've already, in fact, written on the slide? I want everybody to stare at that boxed equation and go, yeah, how are we going to get rid of one of those variables? And look to the other work that we already have on screen and go, is there something that we've written down that we haven't really done anything with? Will we use the volume equation? Yeah, I think that's the thing to use. Yeah, so um, let's do that, right? So, oh yeah, so the volume equation here, we wrote it this way. Okay, so the first circled way has four variables. I mean, v on the left and then LWH on the right, and then we replace the v, so now there's only three variables, just the three on the right. We have this version of the volume equation. I think this is the one you were talking about, right? So that only has two variables because the left side has a 100. The only two variables are w and h. You solve for whichever variable you want, but I think it's, if you solve for w, you got to square root both sides. So I'm going to solve for h. Now, if you solve for w, you can get the same final answer as the way we're going to do it, but it's just, I think you're going to end up writing a lot more. So I think it's the lazy thing to do is to solve for h. So take this equation, divide both sides by w squared, and now that we have h equals this fraction, anywhere you see an h, you can replace it. So right now we're going to write this entire thing, just replacing that h at the very end right there, right? So in the end, we should have c equals the 17w squared is still here, and then 24w, and then replace the h. 24w, and the h got replaced with a fraction. I also, just to comment on it, took a moment to, you don't have to write c of w, you don't have to, but I just, right now, just emphasizing that now that we're down to one variable past the equal sign, I'm just trying to specify that c is now a function with one variable. So that's all this is. I want you to think of c of w just like you think of f of x. So the c is like the f or the y, and then the w is like the x. Right? So at this point, now we finally, right there, have c written down using only one variable. So we could differentiate it, but I don't want to yet. It looks awful to differentiate as written because there's a multiplication sign, product rule, there's a fraction as well. So product rule combined with quotient rule, seems like too much. So it'll make things much nicer for us if we just do the algebra to simplify this first. Just cancel a w on top and bottom, and you'll have still the 17w squared. The 1w that's on bottom is instead a w to the negative first on top, and then I just did the 24 times 100 as a 2400. So this is, I think, a very nice clean version of the cost. So I will just comment that this is the cost, this is the cost, this is the cost, this is the cost. These are all capital C. They all have the same value all the time. It's just this is the most convenient one because there's only one variable there. There's only a w. Now that we have cost written in this format, let's take a derivative. So the derivative is actually relatively nice. No quotient rule, no chain rule. I mean, it's like power rule business, right? So 34w to the first. The minus 1 comes in front. That's why there's a minus sign here. 2400 w to the, you got to lower the power by 1. So negative 1 was the original exponent. We've lowered it by 1 to a negative 2. Let's pause here. Let's just make sure. This is the last thing on this slide, but I want to, any question at all. We're not done, but I just like, is there already, there's a lot that happened, and any one piece of this does not take a lot of time to explain. So ask it, and don't feel bad asking it. What I'm trying to say is there's so many things that happened. I think it's good to just pause and go, wait, where did that come from? Or can you talk about this going from here to there? I had actually a number of questions last section. Only 3 people were in attendance last section, and there were a lot of good questions. So I want with this many people signed in, like there's got to be some questions. So let's just give you a moment, make sure we're okay before moving on. Actually, while we are waiting, I forgot to mention, I would suggest, I hope you're writing down some of this stuff, but definitely, so write down this, C equals that, because we're going to need that later. Okay. A question did come up. Thank you. Let's see. Why do we take the derivative? Why don't we just solve for W? Good question. So if we just take what's circled right now, which is the cost, and you set it equal to 0, right, so to solve for W, first of all, you need to create an equation. I think maybe sometimes, and I've seen this actually occur, so I'm really glad this question's coming up. I actually wish somebody said this last section now. If you take the circled thing over here, let's say you set it equal to 0 to create your equation, and you solve for W, what you've done is you would find the special value, or maybe values, plural, of W that makes C equal to 0. But let's remember what C is. C is the cost. So if you set cost equal to 0, you're going to find out what value of W, or what width would you need for the box to have a cost of 0. Now that's a little unrealistic, is the point, right? Like you're not going to get a box for cost. If C, the variable C is 0, you're going to you're asking what should be the width so that I have a free box. I don't want to pay anything for the box. Now that would be awesome. I get that would be cheapest, but that's literally unrealistic. We're going to have to pay something. So the question is, how do we pay as little as possible? And so the reason we're taking a derivative is, let's imagine if you were to graph C. Now we're not going to graph C by hand. I do have a graph pulled up. We'll look at it in a moment. But without graphing C by hand, there's this graph, and you want to look for where there's a peak or valley in the graph of this C thingy. In order to look for that peak or valley, I guess in this case valley, but still peaks or valleys, at every peak or valley, the slope of the tangent line is 0, right? Like right at the peak, right at the valley, right at a valley, the slope of the tangent line right there is 0. So the reason we took a derivative is the derivative is a formula for slope. Remember, derivative of slope. So it's actually in the next slide. We haven't done it yet, but we're going to set this thingy right here equal to 0. We're going to set the slope equal to 0, right? That's why we took the derivative. Remember, derivative is slope. If we set the slope equal to 0, we're going to detect where the peaks and the valleys are. So yeah, I would love to just set this cost equal to 0, but we're not getting the box for free here. Does that answer the question? And if there's other questions, go ahead and start posting them. I want to make sure. I'm going to wait for confirmation. So we don't want to set this equal to 0. That would be saying that the cost of the box is 0. We're going to set instead the derivative equal to 0, because we want, if we were to, not that we're going to graph it by hand, but if we did graph the cost, we are looking for where there's a peak or a valley. Specifically, we want a valley, but where the valley occurs, that's where the slope, the derivative or the slope is going to be 0. So just making sure we're all. So I hope that answers that question. I'll pause just for a moment for any other questions as well. Or just like, no, I still have a question about this. Yeah, sorry to make everybody just kind of wait, but like there's always a little bit, there's a 5-second delay between the moment I say things. And all right, I think this is now, I will now move on. So, all right, so let's, you've got in this box here, capital C, we just took the derivative, there's C prime. I put C prime at the top of the next slide, okay? So this is the formula for the slope of the tangent line, right? And we want the slope to be 0 to detect any peaks or valleys. So let's take this C prime that we just got and set it equal to 0. You'll notice that as I've often been in the habit of doing, I like negative exponents when I'm thinking about doing derivatives. Like, so right before taking a derivative, I often try to fix things up, have negative exponents so that I don't have to use the quotient rule, because the quotient rule is, it's tedious. So sometimes you have to, but like I use negative exponents a lot. But then when I create my equations, I tend to go back to rewriting the things, using algebra in the denominator. You could totally, it'd be fine if you wrote 34w minus 2400w to the negative second equals 0. That's technically fine. But I find that when I stare at the equation written this way instead, it's just harder to think about what to do next. See, like here, when I see that fraction with the denominator, I go, oh yeah, I got an equation that has a fraction, multiply both sides by the denominator, w squared. You got to distribute the w squared on the left side, so you have 34w cubed minus 2400 equals 0. Now to this equation, we solve for w, add 2400 to both sides, divide both sides by 34, and then you have a w cubed. You got to undo the cube, so we should cube root both sides. So all of those algebra steps in one, you have here w is the cube root of 2400 over 34. And you could just end it right there. I'm using this phrase, is a critical number of C, mainly as a reminder that the work we're really doing, for the most part, a lot of the pieces of it we've already seen like even 2 weeks ago. I'm just trying to, you don't have to write this kind of wording on a quiz or anything like that. I'm just putting it here so that the connection is being made. The point is, this value of w, normally we've been calling this x, but here it's w. This value of w is special, right? This value of w, because this is a spot where the slope is 0, right? We took the slope formula, set it equal to 0, and we solved an equation. So this value of w makes the slope 0. That's where there's a peak or valley. But which is it? Does this value of w make the value of c big, or does this value of w make the value of c small? Is c going to be big or is c going to be small? We don't accidentally want to find a value of w where c is big. That means that's the most expensive box. We don't want that. We want the cheapest box. So we should apply the first derivative test or second derivative test. In this case, I would not really prefer the first derivative test, because in first derivative test, you got to take your c, here we have c prime, but you need the value, you need to see if the c prime is positive or negative both before and after this number. But that number, cube root of 2400 over 34, I don't know what number that is. I mean, it's some decimal, and so I don't want to deal with that. So here's where I think the second derivative test is going to be nicer, as it typically is for optimization problems. We'll have to take another derivative, but that's fine. This actually, c prime up there, is not that bad to differentiate. I mean, we've done worse. Like, there's no chain rule or anything like that. Just some power rule business. 34w differentiates to 34. The negative 2 power rule, differentiate that, comes in front. So negative 2 times negative 2400. That's why there's a positive 4800. W to the lower the negative 2 by 1. You have a negative 3. Okay, this is the second derivative. Remember, the second derivative is going to be useful for getting concavity. What we're going to do is, to apply the second derivative test, plug in this special value of w in. So c double prime of that value of w, cube root of the fraction, and then plug in for w here. The point is, I don't want you to stare at this too long. There's no minus signs here. You might say, well, what about that exponent? Well, that doesn't really count, right? Like, instead of this exponent of a negative 3, it's a positive 3 exponent if you just write this base in the denominator instead. So the point is, there's no true minus signs here other than the exponent, which can be written as a positive exponent. And when you just divide, add, multiply, there's no subtractions, then you know the number has to be positive. And so this second derivative being positive tells you that c has a local min. Right? Why a local min and not a local max? Remember, if the second derivative is positive, you've got concave up. C is concave up, and that concave up picture creates a local min. So this value of w is good. It is a value of w that's going to make the value of c small. Remember, we wanted c to be small. Okay. Sometimes what happens is people sort of say, okay, I'm done with the math, wash their hands of this and then say I'm done. But we're not quite done. We're so close to done. All of this work is relevant, but this is a place that you don't want to don't be done here. Go back to the original question. The wording in the original question was, how cheap is the cheapest box? I've just slightly reworded it here to just emphasize what is the cost of the cheapest box. We should answer the question. All the work up until this line here is totally relevant, but sometimes people stop there as if the question's just a math question, but this is a math question which had an original application. If the boss wants to know how cheap is the cheapest box, we better answer that question. Meaning, well, is the cost of the cheapest box this number that's circled right there? And the point is, it's not, right? This number is not in dollars. This is W. This is in inches, I guess. Was it inches or centimeters? I forget. But that this is the width. Right? So what is this number? It's totally relevant. All the work up here is totally relevant. But this number is not the cost. I've seen people say that this is the cost. I've seen people do things like they'll just take that circled number there, stick a dollar sign on it, because cost is in dollars probably, right? Maybe in yen or who knows, but or euros, right? But sometimes people just take that number that's circled right there and say, that's my cost, that dollars. Wait, but that's a width. So is this number here relevant? Yeah, totally. We now know what number W is. It's this, it's some decimal, cube root of 2400 over 34. But that's not the cost. This is the value of W that causes you to have a box at the cheapest cost. In other words, if the original question is, what should the width of the box be to make the cheapest box, then the answer would be this number with units of inches. But the question was, what is the cheapest box? Meaning, we don't want the value of W. We should take this numerical value of W and now plug it in somewhere to get the value of C, right? So what this value of W up here does is this is the value of W that makes C small, but the question was, what is C? So what we should do is look back to all the previous work. Is there a place where if you know what number W is, that you can immediately find out what C is? And this is the thing that I strongly suggested you write down from a moment ago, that C, written using only W, is this. That was towards the bottom of the previous slide. Now that we know what number W is, let's just plug that in. So the value of the cost, just having plugged in for W there, there, and there, plugging in this special value W that we see. That's all that happened. I'll just maybe erase my markings. It's probably too distracting to look at. Right here, I'll underline it. That in dollars, I've wrote the word dollars. You could, of course, do a $sign either before or after. That is the cost of the cheapest box. Right? So you had to get to W. You had to know, this is the width that creates the cheapest box, but the question is, how much money do you have to pay for the cheapest box? What is it in dollars? You got to go back. That's why I think it's super important to write down what all your variables mean to clarify. How are we doing? This is a good place to pause, make sure that questions are answered. And I do have a picture to pull up in a moment, but I just want to see if there's any questions that I can address first. I guess I will just comment, these are involved, right? So sometimes people stop up to there just thinking this is math only, but this is applied math, right? Math with an application. And so if, the original question that you're tasked with is how much money has to be shelled out to make that box, making it the cheapest possible, you got to answer that question. I do have a graph. Again, I want to emphasize we answered the question without doing any graphing, but I think showing you the graph helps clarify a little bit what it is that happened here. So I already clicked on the link, so I don't have to wait for any loading time. And I typed in the cost formula right here. I noticed that things are a little finicky if I don't use x as the variable. So it says x, but think of every x as a w. And so of course, over here there's this strand like that doesn't make sense with negative x, like -6.5 for an x value or for a width. That doesn't make sense. So we look at this portion of the graph over here, and so the x-axis is width, and then the y-axis is what's the value of capital C. So it's the cost, and we wanted the cheapest cost, so that's this point down here, right? And so you'll see that this point, this local minimum that we just found, 4.133, that is that cube root of that fraction, whatever it was, right? So 4.133 is the value of the width. That is the choice of how wide the box should be to make the cheapest cost box. And then what is the cost of the cheapest cost box? That's what this y coordinate here represents, right? 871.08, that's the y value, or that's the capital C value. So if I go back to over here, that's what this is, that 871 number, right? That is the number of dollars for the cheapest box. I will make the following comment as well. I said the comment yesterday, it probably didn't make a lot of sense yesterday, but like whenever you answer the original question, you know, you want to go back and look at your old work and go like, okay, in this case, I know what number W is, but I need the number for C. And so you want to look back to all your previous work. And somewhere in your previous work, you got to ask yourself which equation. I want you to be as lazy as possible, but you just need to scan your work. Excuse me. And ask, if I know what number W is, how can I quickly get what number C is? And I promise that somewhere in your old work, you actually already had an equation that you needed. So here's the tip. I said it was here yesterday. I didn't say much about it. Sorry for the typo in original, but when answering the original question, first of all, go back and go, wait, which variable answers that question? In our case, it was capital C. We needed the value of capital C in the end. And the point is, you probably already solved for that variable. Not just probably. In fact, if optimization is done correctly, you can go back in your work. In fact, even in this question, every variable was solved for. We have an equation where V was by itself, where C was by itself, where H was by itself, where L was by itself. I mean, every variable was by itself. And sometimes in multiple different ways of writing. So look for an equation that's most convenient for you, or you can start over. You can go to the beginning and start. I mean, the point is, as soon as you know what number a certain variable is, you can start plugging in, getting the value of plenty of other variables, but there's usually a most convenient equation. And so what I'm saying is try to use that one. Overall, the big picture, again, is to find mins and maxes. You need to get the objective on one side with the other side of the equation just having one variable. I'm going to give you some time to work, but I do want to just, from the sheet of questions here, I'd like to just draw a picture of question 10 together. So I did screenshot question 10, and let me read it out here that we're going to make a box. This is an open top box, so there's no top of the box. So normally a box has 6 sides. This will only have 5. We're going to make this by cutting squares out from 4 corners of a 12-inch by 12-inch sheet of cardboard. So here's like that sheet of cardboard, 12-inch by 12-inch. So 12 there, perhaps, 12 there. And we're going to cut squares out from the 4 corners. So here, what I'm trying to get at is like, there's a square here. Using scissors, you're going to remove that square, and then the same square there, the same size square there, and then the same size square here. So those 4 shaded parts are like, you chop those out. And then, having chopped those out, you bend up the sides. So if there's no cardboard in this shaded region anymore, then you can, like right where this dotted line is, okay, here's a second dotted line and a third one and a fourth one. You can fold up these. I'm shading these in sort of slanted right now. You can fold these up, the slanted pieces, as flaps. So like, for instance, I'm drawing on a tablet which is completely flat on a table right now, and if I fold where those dotted lines are, those cardboard flaps, I could fold them up, and then I'd create a 3D view. The flaps will be closer to me. The question then is, so that should create a box, and the question here is, how large should the squares be cut to make the box hold as much as possible? So let's call the side of the cut C here. So C is representing just one side of the square, and I could label, of course, it's a square. So I mean, I could label this down here as well. I could label this over here. I don't want to do it everywhere, but I think that's enough places of labeling C, the size of the cut. And then let's look at the question here is how large should the cuts be made? So what should be the value of C? And then you'll take a look here to make the box hold as much as possible. Now this is language that hold as much as possible. We're talking about we want the volume, like, okay, as much as possible, max, sure, right? But maximize the volume. That's hold as much as possible is trying to get at, right? Maximize the volume. So, okay, we are dealing with a box, and in this box, you've got the volume is equal to L times W times H, right? So we want to maximize volume. Well, you got to solve for V. Fortunately, V is already solved for right there. The problem is, of course, there's three variables here. But I want you to think about this. If you fold up, this flap, then as you fold this up, this distance right along there, that is the height. So that's C. That's right. And then what about the length and the width? Well, let me draw in a new color. This right here could be the width, for example, that blue line segment. And then maybe this one right there would end up being the other one, the length of the box, right? It turns out that both of those blue segments should be the same size. It's because, well, you started with a square, a big cardboard square, and then you cut out squares. Now, what is this? So L equals W, but what is that actual size? Sometimes people want to say it's 12 minus C, but that doesn't actually work. If you take a look, 12 is this entire thing all the way from top to bottom, and if I just slide this blue piece over, you'll find that C, which is just right along here, well, there's another C down here. So instead, you have 12 minus C, or in other words, 12 minus 2C. So I would replace the H with just a C and replace L with 12 minus 2C, replace W with 12 minus 2C. So maybe you want to try this problem or another one from the list in the last 6-ish minutes. If you've got this picture down, you want to try that one, cool. What I think I'll do is I'll leave the list of problems, at least as many as I can fit on screen here, like questions 4 through 14. And I'll take questions if you have any, but I would work on one of these. I mean, your other option is if you just want to leave the room early, then, when you get stuck on optimization problems, I guess you'll have to come to office hours or the learning center or something. But this is an opportunity to get stuck right now. And then if you do, you can ask a question and get an immediate answer to your question. So pick a question, even if it's problem 10 that we just drew a picture for. All right, there's just about 1 minute remaining, so just a quick round of announcements. You may have heard it already, but I think it's just good, both beginning and end, in case somebody's just getting to the end of a recording, for instance. Just to say, tomorrow there is an online quiz, so please remember to do that. And then you heard the longer version earlier, but please do I know you've got a lot going on. But please try to avoid just starting a web work assignment the day that it is due, because that is typically now 6 days later than I want you to start looking at the assignment. Otherwise, I hope you'll make it into office hours, or if the times don't work, please email about an appointment, or visit the Murphy Learning Center online as well. If one of the issues is bandwidth, and I get that, you can always we can do an audio only thing. It's not ideal, I get it, but that's an option of like call the office phone number, and if it's during office hours and we're connected that way, we will figure out something to do for writing down some things. Okay, I think I'll call it a day. See you for office hours later today or for class tomorrow.